Students, today we shall understand the next property, next concept of application of Gauss theorem, and that is the electric field due to charged spherical shell at different positions. So let us see what exactly the derivation is all about. This is electric field due to a charged spherical shell. Students, this is actually the heading, but this is an application of Gauss theorem. Without application of Gauss theorem, we cannot derive this. But if we use application of Gauss theorem, then we'll have to derive the same, where we have to consider a spherical charge shell first form. So there is a spherical charge shell, students, you have to consider, where we have to provide some charge on its surface, which will be resting on the surface of the spherical body like this. And you know, if this is a spherical body, charge must be lying on its surface, so it must have a surface charge density. It must have a surface charge density, students. So if suppose this is body and its radii is r capital, say its radii is r capital, then what happens? So we have to enclose this entire charge body first, so that we could get flux, and then only we'll apply Gauss theorem. So let us see how. So we have to assume a spherical Gaussian surface around the same charged body. If we assume a spherical Gaussian surface which encloses this charged body inside. And if it is considered as a Gaussian surface, it must have some surface area. And if it has some surface area, then its radii will be taken as a small r. So first condition to be written down as small r greater than capital R. Small r greater than capital R. So let us see. If this is a Gaussian surface, we have to take a smallest part of the Gaussian surface on the spherical body. This shows the direction of electric field through the Gaussian surface. This is small area vector, students, and that is theta. If it is theta, which is making an angle between E and ds, this is a small Gaussian surface, and we have to find out the flux through entire Gaussian surface, although we have taken a smallest part. So it is nothing but an integral calculus method. So how it is taken into consideration, let us see. So if we say that this charge body, which has sigma charge density, must be enclosed by a Gaussian surface of radii small r, so therefore small r will be greater than capital R. So let us assume, so let us write something. Let us assume a Gaussian surface around a given spherical charged body of radii capital R. Then what happens, students? Let us see. Then we get flux, As you know, in the previous videos, I've already told you that whenever we want to find out the electric field, first of all, we have to find out the flux through the Gaussian surface. So first condition is finding out the flux through Gaussian surface. Let us see how. Then we get flux through Gaussian surface. Flux through Gaussian surface as phi equal to E into ds. Students, we have to find out this, and that is cos theta, you know. But for maximum flux, we know that theta must be 0 degree. This theta must be 0 degree so that we could find out the maximum flux. So we have E into ds integral calculus, E into integration of ds, and finally phi equal to into s. For students, you know that s is the surface area of the spherical body, which is a Gaussian surface, because we have considered this one as Gaussian surface. So this has to be the area of Gaussian surface as. So its surface area, you know, will be equal to 4 pi small r square. Why? Because Gaussian surface has got the radii small r. That's why its area would be this. So finally, we will find out the flux as electric field into 4 pi small r square. This is the concept. This is taken as equation number 1 now. Afterwards, we need to write down something else. We know once we find out this flux through the Gaussian surface, then we have to find out the flux due to enclosed charged body, and then only we'll apply Gauss theorem. So what do we write here? Now, using Gauss theorem, students, we write down Gauss theorem as flux phi equal to q by epsilon naught. But as you know, q is given as sigma into s. But students, must be aware of one thing, that this surface area and that surface area are different. It will have the radii r capital, although this one has the radius small r. So now we are talking about the enclosed charged body, and that's why its surface area must be taken as S dash, which is a different than the Gaussian surface. So therefore, we will have Gaussian surface as S dash. So sigma into S dash, epsilon naught is there. So you know S dash is the Gaussian surface and S dash equal to 4 pi capital R square, students. This is capital R square. So what do we get? Let's see. Phi equal to sigma into S dash means 4 pi capital R square whole upon epsilon naught. This must be taken as equation number 2 now. This must be taken as equation number 2 now. Now what should we do? We'll have to compare these two equations, because this flux or that flux, both are given for the same body. Henceforth, both the flux will be same, but in different type of terms it is given. That's why we have to compare these two equations. Let us see how. Now we will do the same. Let us see. Fine. Comparing equation number 1 and 2. Comparing equation 1 and 2. See what do we get. we get sigma into 4 pi capital R square upon epsilon naught, and this was the equation number 2. But what was the first equation? It was E into 4 pi small r square. That was the same formula. So what do? We'll have to cancel these two values, and then we'll have to find out the electric field. What will be the electric field then? See what happens. Sigma by epsilon naught, capital R square was there only. The small r square will be taken in the denominator. Finally, we will get the relation for electric field when charge is taken outside the charged body. So we will get the electric field outside here somewhere. So this is the formula. Now we'll take out the case number 2. So what is this is proved. Now we take the case number 2. What is case number 2? When small r equal to capital R. Actually what happens? Small r equal to capital R means we have to remove these two terms and we have to consider this entire body itself a Gaussian surface. We have to consider this entire body itself a Gaussian surface. So the body will have the same radii for Gaussian surface as well as charged body. So in that way, this body behaves like a Gaussian surface even itself. Henceforth, small r will be equal to capital R. Therefore, from previous relation, we get E equal to sigma by epsilon naught into capital R square upon capital R square. As you know, this is taken into consideration. Small r will become equal to capital R. Hence, we get small r as capital R here. Finally, this will be getting cancelled, and then final relation would be this. Everyone must have understood, student. I think all girls and boys, you must have understood this entire part. So this was the case number 2, when the charged body will be behaving as Gaussian surface itself, and that's why we'll have to consider point P on the same surface of the body. Now case number 3. What is case number 3 now, students? Case number 3. Let us see. Case number 3, when small r will be less than capital R. What happens? We have to take that point inside the body itself. Say point P lies somewhere inside the body. Means it is a hollow space, If it is a hollow space, then we have to take something different. Let's see how. We'll have to take something different. Let us see how. See, students. If point P lies inside the hollow structure, then we know that we need to write down. We know that a free charge cannot exist inside a hollow body in air. Thus, Q inside will be 0. And if Q is equal to 0 inside, means there is no charge inside which could be existing, because whatever charge is given to the body will be coming on the surface itself. That's why no charge will exist inside the hollow space anywhere. So, therefore, final result will be E inside is also 0. If there is no charge inside, then there is no field inside. So finally we will get electric field inside the hollow space would also be 0. So this particular thing, this particular phenomena will be known as electrostatic shielding. This is called, this is this phenomena, actually this phenomena is called electrostatic shielding. Electrostatic shielding. That's all. So this is done with all the cases for electric field due to charged spherical shell. Now we go for the graphical statement, graphical representation for entire phenomena, all the processes. Let us see how. Graphical representation for the same graphical representation is, if suppose graph is formed between electric field if graph is formed, students, if we represent graphical representation likewise, then we have to form a graph between small r, which is variable, and electric field. So you know, inside the center, inside the body, from center to any of the point till it reaches to the surface, its electric field will remain same, that is equal to 0. So if we take hollow body, then we know that there is no existence of the electric field inside. That's why from center to the any point before the surface, electric field will be 0 only. As soon as it reaches to the surface, its electric field will be maximum. But if it goes beyond the surface, so it can go any distance. And that distance will be outside the spherical shell. Therefore, here electric will be gradually decreasing. Therefore, we get the graph like. We get the graph likewise. If suppose we have got the graph, this is the electric field 0 when R is less than capital R. Means wherever R is less than capital R inside the spherical shell charged body, R will be less than capital R, then electric field will remain 0. But as soon as it goes to the surface exactly, its electric field will be maximum. In that way, in that point, R will be equal to capital R and its electric field will be maximum. But what happens afterwards? As soon as those passed beyond the spherical charge body, it goes to distance R, which is greater than capital R. Then it go to infinite even. So its value will be decreasing likewise. It will never meet to this point because it can go to infinite point. Electric field can be existing till infinite. So its value would be decreasing exponentially. So this could be given as E inversely proportional to R square provided the small r will be greater than capital. Students, in this way, we have to find out the graphical representation for the charged shell as far as electric field and distance is concerned. In this way, we have finished this entire part of electrostatic 1. Okay, thank you.